So remember my rules. We want to balance hydrogen and oxygen last. So let's try to balance everything else. So going through the reactant side, I notice that there's a P, a phosphorus. Then coming on the other side, I see that there's another phosphorus. But wait a second. This phosphorus is kind of tangled up on the inside of these parentheses. Sometimes you will see chemical compounds, chemical formula, that contain parentheses. And sometimes there and with a subscript outside of the parentheses. Let me tell you a little bit about what the parentheses mean. That means that the substance inside the parentheses behaves as a unit. It behaves as a specific substance. So PO4, 1 phosphorus and 4 oxygens, we could maybe show it like this. The fact that it is in parentheses here tells me that this structure, PO4, behaves as a unit of bonded atoms. It always goes together. And when I see it in parentheses with a subscript 2, what do you think that means? It means that there is, in this chemical compound, not a single PO4 unit, but rather 2 of them, bonded to 3 calcium atoms. So I would draw it something like this. So this could be one way, and this is not entirely accurate, but you get the idea. This could be one way of drawing this chemical compound. 3 calciums, and then 2 units called PO4 that always go together. Each one made of 1 phosphorus and 4 oxygens. PO4, PO4. There are 2 of them bound to 3 calciums. That is what the parentheses mean, and that is why there's a subscript on the outside of them. So, how many phosphoruses do I actually have on my product side? Do I have 1? No. There is a single phosphorus in this unit, PO4, but then I have 2 of those. I have 2 phosphoruses. And so I would know that I would also need 2 on my reactant side, when currently I only have 1. So I can put a 2 right here. Now listen, there is another way of looking at this whole thing. If I recognize that PO4 is a unit that goes together, I can just balance it all at once on both sides of the chemical equation. There are 2 PO4s on the product side, therefore I need 2 PO4s on the reactant side. So this 2 takes care of the PO4, the whole thing, the whole unit. 2 PO4s, 2 PO4s. I have 1 calcium over here. I have 3 over here, so I know I need to put a 3 right there. That just leaves the oxygen and the hydrogen, which is a little bit tricky. Now, if you're following me with the idea that PO4 is functioning as a unit, then technically we've already balanced these oxygens in this PO4, right? The oxygen contained in phosphate, PO4, has already been balanced. So when I go to balance all the rest of the oxygens, I don't need to worry about it. Let's balance the hydrogens now. I have how many hydrogens total on the reactant side? Think carefully about this. Well, right here, I would have 6. Every single H3PO4 contains 3 hydrogens, and I have 2 of them now. So that's 6 hydrogens. How about from this substance? How many hydrogens do I have? Well, each piece of CaOH2 contains 2 of these units called OHs. So, in a single CaOH2, I would have, remember what we do with this subscript in the parentheses, you distribute it, I would have 2 H's. But I have 3 CaOH2s. So how many hydrogens do I have total? I would have 6. hydrogens from this substance. 2 hydrogens per CaOH2 because of the subscript outside the parentheses. But then I have 3 of these, which makes a total of 6 hydrogens. So 6 hydrogens here, 6 hydrogens here. I have a total of 12 hydrogens on this left side. I only have 2 on the right side. How can I get 12? Should I change the subscript from a 2 to a 12? No. H12O is not even a thing, so that's definitely not what I do. Remember, you add a coefficient. What coefficient would I add to get 12 hydrogens on the right side? Well, every 1 water molecule contains 2 hydrogens, so I'm going to need 6 water molecules to get a total of 12 hydrogens. 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, 2, 4, 6, 8, 10, 12. I have 6 pieces, each containing 2 hydrogens for a total of 12 hydrogens. I have 2 times 3, 6, 3 times 2, 6, 12 on the left side, and now I have 12 on the right side. So now when we go to balance oxygen, remember, we can think about it like this. I've already balanced the oxygen that's found in PO4. PO4 remained PO4, phosphate, stayed together as phosphate on the left and the right side of the equal sign, or of the reaction arrow. So I balanced it all together as one unit. 2 phosphates, 2 phosphates. So when I go to balance the oxygen, I can ignore it because I can consider that I've already balanced it. So oxygen then only shows up right here and right here. How many oxygens do I have from this substance? Well, every piece of CaOH2 has 2 OHs, which has 1 oxygen. So I have 2 oxygens, but I have 3 of these. Therefore, I would have 6 oxygens. How many oxygens do I have from my water on the right side? I have 6. Therefore, the oxygen is also balanced. This one was tricky, but we should always go back and check our work to make sure that we've done it correctly. How can I check my work? Just go through every element and make sure you have the appropriate number. How many hydrogens? 2 times 3 is 6, plus 3 times 2 is 6, 12 hydrogens. Sometimes it's very helpful to make a list. For those of you who have a difficult time keeping track, staying organized, I highly recommend you make a list of your elements. I have 12 hydrogens. How many on this side? 6 times 2, 12 hydrogens. How many oxygens on the right side? 6 oxygens. Now my equation satisfies the law of conservation of mass. What does this equation tell me? It tells me that these substances must combine in a 2 to 3 ratio to produce these substances in a 1 to 6 ratio. If you've taken biology, this reaction may look familiar to you. C6H12O6 is a chemical compound called glucose, and this is basically how your body extracts usable energy from the food that you eat. Glucose is kind of a high energy substance. By reacting it with oxygen, your body is able to get the energy out of the chemical bonds of glucose and put it to work. And the waste products of that reaction are carbon dioxide gas, which you breathe out, and water. Right now, this equation is awful. It's not balanced. So I need to go through and balance it. Remember, save hydrogen and oxygen for the end. So I have 6 carbons on the left side. I need to add a 6 right here. I have 12 hydrogens. I need to add a 6 right here. Now I need to count up all my oxygens. I have 1, 2, 3, 4, 5, 6, 7, 8 oxygens in total on the left side. How many do I have on the right side? I have 6 times 2 is 12, plus another 6 is 18. Yikes, I have 18 oxygens over here, and I only have 8 oxygens over here. How can I get this to balance? Should I try to adjust this substance to get the oxygens to start increasing so I can end up with a total of 18? No, because if I start adjusting this substance, that's going to screw up my carbons and hydrogens. So I don't want to have to do that unless I absolutely need to. So is there something else I could do? Yeah, I could try to adjust this. So is there a coefficient I can put right here that will bring my total number of oxygens from 8 to 18? Think about it. Yes. If I also place a 6 right here, 6 times 2 is 12, plus the 6 here gives me 18 oxygens. Now it's balanced. This is how you balance this equation. C6H12O6, for every 1 molecule of glucose, we need 6 molecules of oxygen to create 6 molecules of waste CO2 and 6 molecules of waste H2O. That is how you balance chemical equations. Why do we balance them? So that we can satisfy the law of conservation of mass. You cannot end up with more building blocks, with more matter, with more atoms than you began with. You cannot end up with fewer than you began with. You cannot create, nor can you destroy matter. You can only rearrange it. And that's what chemical equations show. They show that old bonds between reactants get broken apart, the atoms rearrange themselves, and new bonds get put together. And a chemical equation models that. Next time we're going to see how energy is involved, how energy changes are involved. Remember, to break apart all the old chemical bonds, what has to happen? We have to put energy in to rip the bonds all apart. What happens when new bonds form? We get energy out as the system reaches a lower potential energy state as those bonds form. So we have to add energy in, and then we get energy out. The system loses energy. And we will begin analyzing this in more detail next time.